Without further ado, please take it away, Stephen.
All right, thanks, Will. So we're going to be talking today about inference for prediction problems or uncertainty quantification for prediction problems. And in particular, we're going to be able to use kind of complex machine learning models along the way. So predictive inference for black box machine learning models. Before I go farther, I'd like to say thank you and acknowledge my, my co-authors here. So Anastasios and Liwa, who are both on hand to answer questions in the chat, and Jitendra and Mike. So it's been great to work with these guys. So to start the conversation today, I want to introduce kind of a classification problem that we're going to think about. So this is a real classification problem. It's medical images, and they're each one of 3 classes. Some of these chest x-rays are from class normal, some are from class COVID-19, and some are from class pneumonia. All right, and then what I did here, this is real data. I fit kind of a deep learning model to predict what class they're all from the left, the center, and the right. On the left, the model predicts COVID-19. In the center, it predicts pneumonia, and in the right, it predicts pneumonia. Okay, so these are the point estimates from my deep learning model. And our sort of kind of motivating question here is this the right information from the doctor? All right, so in this case, it so happens that the center and right images are misclassified, they're incorrect. The left image was correctly classified. This is not by itself a problem. I mean, we know we're going to have some errors, but we would kind of like to have a little bit more knowledge about when we're likely to make an error or not. Okay, so our sort of question for today is going to be, when can I communicate some sort of uncertainty information to, in this case, say the doctor, but maybe some downstream module of my predictive system. Okay. So I don't think I have to convince, this audience that, this is somewhat limited output and that I would really prefer to have something more. You can think of perhaps probabilities. So maybe I would guess, maybe my model would say that, oh, I think this is 80% likely to be COVID-19. This is 60% likely to be COVID-19, and this, or pneumonia, sorry, and this is 40% likely to be pneumonia. So output like this would be useful, but then my question would be, what do these numbers mean? What does 40% mean? What does 60% mean? What does 80% mean? Okay, so, this is good. This is going to help me this is going to communicate that this image on the left is, for example, an easy image. That's true in this case. You can't really tell with your eye, but the model knows this is an easy image. This image in the center is actually a moderate image. It's kind of a little bit confusing. And then this image on the right is actually a very challenging image for this model to predict. Again, you can't necessarily tell that, but the model is kind of like internally aware of this. And so the question is, how can I sort of make that, make that rigorous? How can I make statements like that have a particular statistical guarantee so that when I kind of use this output and I say, this is a pneumonia and it's a moderately difficult image, I can tell you exactly what I mean by that, okay? So we're going to need some uncertainty quantification. I need to rule in or rule out bad outcomes. It's not enough for me to say it's COVID-19 or it's pneumonia. I need to give you something a little bit more. And this talk is going to explain, a certain way of doing that. All right, so prediction here is important, like I said, but we also need inference. So to kind of set the stage a little bit more, I'll bring to your attention this kind of classical thought piece in statistics by Leo Breiman. It's called Statistical Modeling the Two Cultures. And Leo Breiman here is commenting on kind of different models that we use in statistics, and he's drawing a distinction between stochastic data models and algorithmic models. Stochastic data models here would be more kind of like generative models, like perhaps a linear regression model where the terms all have some sort of scientific meaning. And then algorithmic models here might mean something like random forests, or in our case, neural networks. All right, and so Leo Breiman's point here is that there's a lot of great features about stochastic data models that statisticians love. They're interpretable, they're mechanistic, I can have kind of inferential statements, but some situations require, other tools, like in this case, what he's calling algorithmic models would all be calling black box predictive models in this talk. So the cases where we really, really want these algorithmic models are cases where they have excellent prediction accuracy, such as in classification problems with, say, images. One thing that maybe leaves us a little bit more unsettled about using these black box models is we don't have as well developed of a tool set for kind of doing inference. And that's what this talk is going to talk about. We're going to discuss inference for these prediction tasks, with an eye towards these complex algorithmic models. Okay. So, these scientific and sensitive applications, we really need this inference. The main challenge here is that these models are very complicated. So state-of-the-art predictive models in something like image classification are very, very complex. So here's a kind of schematic of a pretty simple neural network. Here are some statistics about a relatively state-of-the-art neural network. So this is ResNet 152. It's actually about 5 years old, 2015. It has 500 layers and 60 million parameters. And if you want to download the model, it's 250 megabytes. So, this model is the size of, some data sets we sometimes use. Right. Okay, so if I want to talk about uncertainty with an object like this, with a very complex model like this, it's going to be challenging, right? I mean, it's not necessarily straightforward. So what are the options here? I mean, can we just ignore the uncertainty in these prediction tasks? And the answer is, of course, this is not a good thing to do. I don't think I need to convince you of that. Should we kind of abandon these models or look for other models? I would say right now the answer is no. These kind of complex models have much better predictive performance for many tasks. And so, we can't just, fall back on some simpler model for convenience here. We really need the good prediction accuracy that we get from these models. So how could we go about sort of getting uncertainty here? A initial statistical approach, an approach that might be sort of a first instinct for many of us would be try to analyze these models like we do with, say, linear regression, where I can tell you about the sampling variability of each of the coefficients. This is going to be very hard in a case where I have 60 million parameters, right? So if I have 60 million parameters, the approach of kind of analyze the sampling variability of each of the 60 million parameters is going to be very, that's a tall order. So, excuse me. So the approach we're going to take in this talk instead is we're going to kind of build a meta procedure, like a wrapper procedure, something like cross-validation. And it's going to work with these black box models. So it's going to kind of, as input, you take some predictive model. It doesn't matter what it is. It can be very complicated. And then by kind of feeding in inputs and looking at outputs, we're going to be able to analyze the properties of that predictive model. All right. Okay, so more formally, the way we're going to kind of talk about uncertainty in this presentation today is we're going to use prediction sets. Okay, so we're going to return sets of outputs rather than simple outputs. So recall in this example, I'm plotting here these point estimates. So on the left, I might guess it's COVID-19, in the center pneumonia, and the right pneumonia. And we saw that this kind of single point output was a little bit limited in the information that it's communicating. So instead, we're going to return sets. So in this classification example, that means sets of labels. So I'm going to return multiple labels. It could be one label if I'm very confident, but it could be multiple labels if I'm uncertain. And this will kind of, tell me how hard or easy an image is. So for example, on the left, this is, real data. This is a real model. The output here is COVID-19 by itself. So the prediction set has one element and it's COVID-19. You should interpret that as meaning I'm very sure that this output is COVID-19. In the center, the prediction set has two elements. So the model here is saying it's either pneumonia or it's COVID-19. So this is a kind of more ambiguous image than the one on the left. The right-hand image here, the prediction set has three elements. It's either pneumonia, COVID-19, or normal. Those are the only three classes it could be. So in this case, the model is saying I really do not know what's happening with this input. So this is, again, kind of communicating this information that the left image is an easy image, the right image is kind of a moderate image. Oh, sorry, the center image is a moderate image, and the left is a challenging image, okay? And the reason we're going to take this approach here with these prediction sets is because we're going to be able to give statistical guarantees about these prediction sets. So I'm going to be able to make precise finite sample statements about the error rates of these prediction sets, okay? Which we will discuss next. So I'm going to return sets rather than one output. I'm going to return a set of outputs, and that set of outputs is going to have some statistical error control property. Okay, so this is kind of building from this great line of work called conformal prediction. Conformal prediction started kind of in the late 90s by Vladimir Vovk, our discussant today, among others. And recently there is also kind of another large line of work from this group at CMU. Okay, so conformal prediction is a technique for producing sets, like I showed you on the previous slide, that have a very special property. These sets have the property that they contain 90% of the labels of future test points. Okay, I'll say that more precisely after I introduce some notation. So I have data xi, yi, and they live in, cal x, cal y. X is the features, y is the response. So in the previous case, y is the label. And then I have these points 1 to n plus 1. N plus 1 is my notation for a test point. So n plus 1 is a fresh test point from the same distribution that hasn't been used before. Okay. The only assumption here is that these data points are IID. This can be relaxed even, but for now they're IID. So they come from some distribution, they're independent samples, but I'm not telling you anything else about that distribution, and I'm not making any restrictions about that distribution. Okay, now what conformal prediction does is it gives us it's a kind of a set of statistical techniques for giving these prediction sets that map X, so cal X, the input space, to 2 to the Y, so subsets of the label space. So it's a set of labels like pneumonia, COVID-19. And it has the following property: the probability that I got the right label is 90%. So the probability that yn plus 1 is in txn plus 1, txn plus 1 is the set, it's my prediction set, is 90%. Okay, marginally over yn plus 1, xn plus 1, and the randomness in the calibration of t. Okay, so this is a pretty amazing property. I can't really say enough good things about this. Just to kind of communicate why this is so special and so useful, you get these finite sample coverage guarantees. So I get this 90% almost exactly. Okay, it works for any predictive model. So I can use my deep learning model or my gradient boosting model or my random forest or anything like that. And it works for any distribution. So all I'm assuming is that I have some IID data points, and there's no other assumption. There's no restriction on that distribution, and I don't need to know what the distribution is. Okay. So this is pretty amazing. And this kind of applies to a lot of different procedures in the conformal world. Today, we're going to talk about sort of an extension of conformal prediction that handles a couple of, I'll say, shortcomings or limitations of conformal prediction. The shortcoming I'm going to talk about today is that this notion of error, which is the probability that yn plus 1 is in the prediction set, is sometimes a little bit limited, or is sometimes not the right notion of error. Okay, so you can think about this as kind of a 0-1 loss, where I incur loss 1 if I miss the correct label, and I incur loss 0 if I don't, if I contain the correct label. And then here I'm saying, I get the correct label 90%. So this 0-1 error is sometimes not the right error. And in particular, when I have high dimensional outputs, so not inputs, outputs, I'm predicting something y that is like a high dimensional object. This 0-1 error might not be the right thing. And I'll show you an example of that on the next slide. So today what we're going to talk about is, sort of a generalization here that will address these points. All right, excellent. So here's an example where a kind of naive application of conformal prediction won't give you the right thing. So if this is a tumor segmentation task where I'm mapping images to a subset of pixels. So an image here lives in R to the d by 3. The 3 is for 3 color channels. And the label here is a subset of pixels. So it's a binary mask on d to the d. It's a subset of pixels. D here you can think of as, somewhere between 100 and 1,000. So this output space is very large. It has dimensions, say 100,000. Okay. All right. So what I'm showing you on the right is, for example, an image. So I give you this particular image and I ask you which pixels are associated with a tumor. And in this case, the way the colors are encoded here, white is a true tumor, black is just some background image, and then blue is a spurious positive. So I ran conformal prediction and it picked up the blue parts as tumors for a reason I'll kind of elaborate on now. Okay. So what I'm plotting here on the right is I fit some deep learning model, and then I use conformal prediction to give me prediction sets, just like I was showing you on the previous slide. White here is the true tumor, like I said, and then blue is a spurious positive. So what you see here is that conformal sets cover most of the image. And this is a bad thing, right? Like I'm telling the doctor that this whole region is tumor and this region is tumor, right? So I'm telling them almost the entire region is tumor. And so this is not the ideal output. Okay, and it turns out what's going wrong in this case is not the model. The deep learning model that I fit is not a problem. It's perfectly serviceable, and I'll show you some other outputs soon with the same model. The problem here is that the kind of calibration scheme I'm using based on conformal prediction is asking for a kind of very sharp error notion. Okay, So the way that conformal prediction is working in this particular case is it's trying to fully cover 90% of examples. So it means I'm on 90% of images, I fully cover the tumor. Okay, but remember the tumor pixels live in this huge high dimensional space, and so asking to get every single tumor pixel is very challenging, right? It's a very demanding task, and that's what's going wrong. So if you look, it's hard to tell, but there's actually a bit of red right here. Okay, red means it's a false negative, which means red is a bit of tumor that I missed, that my model missed. So if you look at these 10 images, conformal prediction says, okay, great, I got 9 of them right and I got 1 of them wrong, which is exactly what I asked conformal prediction to do. Okay, but the problem is that was just too demanding of a task. I asked it to not miss any pixels from 90% of images. All right, so from this perspective, you can sort of see that the problem was that this notion of error is a little bit too brittle. Asking it to fully cover all of the tumor pixels on 90% of the tumors was maybe the wrong thing to ask. And so we're going to talk about a sort of slightly different version of error control. All right, so the version of error control that we are going to talk about today, that I'm going to introduce, kind of uses a general loss function or a kind of broad set of statistical error rates. And in this tumor segmentation example, what we're going to do is we're going to cover 90% of the tumor pixels on average. Okay, so this is a more relaxed statement than the previous one, which was to fully cover 90% of images. Instead, I'm going to try to get 90% of tumor pixels right. I know sometimes I'm going to miss pixels around the edge, like that's not going to bother me too much. I just want to get them kind of mostly right. Now on the right-hand side here, you can see our output using exactly the same deep learning model. So it's kind of a apples to apples comparison. I'm just changing the calibration criteria. And you can see that the output here is much better. So black here is background, which means it's not in my prediction set. White is correctly detected tumor, and blue is spurious positive. For example, there's a little bit of blue here. And then red is missed pixels. There's a little bit of red. But in any case, you can see that this procedure is much less sort of conservative. It's returning much smaller prediction sets, but it's still getting most of the tumors, and in fact is getting 90% of the tumor pixels. So I get 90% of the tumor pixels, and it's sufficiently powerful to be kind of usable downstream for other tasks. Okay. All right, so I'll show you how to do things like this in the talk today. The great properties we're going to have finite sample risk guarantees with any model, any deep learning model, for example, and then any unknown underlying distribution, just like conformal prediction. The difference or kind of the delta of today's talk is going to be about using other error notions, such as this 90% of tumor pixels, which is a false negative rate. All right, so in order to kind of explain the main results of today's talk, I'll need to introduce a bit of notation. So we're going to start off with a predictive model, f hat, and f hat, it has no restrictions on it. So f hat in these previous examples was a deep learning model. In general, it can be kind of anything. In the tumors example, remember, it took inputs x and it mapped them to kind of a score, a 0, 1 valued score for each pixel. So it's a deep learning model. And then for each pixel, it gives me a number between 0 and 1 that's an indication of how likely that pixel is to be a tumor. You could call these model probabilities, but I want to emphasize that these probabilities do not have any particular property, associated with them. Okay. Now we're going to have a little bit of fresh data, which I have introduced previously. I'm going to have n new data points that were not used to train the model. So I did say sample splitting. I used most of the data to fit the model. And then I saved 1,000 points for this calibration procedure, which I'll show you today. The calibration points need to come from the same distribution as the test points. But other than that, there's no restriction. Okay. No restriction on what that distribution is. What we're going to do today is we're going to train these set valued predictors T that take inputs X and map them to this space Y prime, cal Y prime. Cal Y prime is going to be some space of sets. Okay. And this predictor, I should say, is going to be, it's going to be mostly built on top of the deep learning model. So I'm not training it from scratch. I'm just going to kind of extract information from my base model f hat. Okay, and what I'm going to do is I'm going to take the inputs and map them to outputs in some set space Y What is y prime? In the tumors example, it's a set of pixels. So y prime is just possible sets of pixels. And the way I constructed this set in the tumors example here on the right is that I have this deep learning model f hat. For every pixel ij, it estimates some probability, model probability, some score, and then I threshold that at some number lambda. So I take all of the pixels that my model estimated were of kind of significance greater than lambda for a kind of strategic choice of lambda. Okay, so all I did is I took my deep learning model and I threshold the output. All right, and then we're going to talk about statistical error rates in these last two lines. So I'm going to have some loss function. The loss function has two inputs. It has a true response y and a prediction that lives in y prime. And with each true response and prediction set, you have some associated loss. In the tumors example, the loss of y and s is the prediction, y is the ground truth, is the fraction of tumor pixels that I missed. Okay, so this is fraction of true tumor pixels that I did not return to you. Okay. Now we're going to control the expectation of this quantity, which we'll call the risk. In the tumors example, this is the false negative rate. It's the expected fraction of tumor pixels that I miss across images. Great. Okay. All right, so with this notation, I can kind of introduce our notion of error control. This is going to be the statistical property that I'm going to give to you at the end of this calibration procedure. It's going to be the following. I'm going to have this function here that maps x to y prime, and it's going to be a risk controlling prediction set if the probability that the risk is greater than gamma is less than delta. Okay, and gamma and delta here, they're chosen in advance by the user. So in the tumors example, gamma here was 10%. It was a 10% false negative rate. Right. So just to visualize what this kind of definition means, what we're going to ask. So t here is going to be, it's a random function because it's trained on data like everything else we do. So r of t, the risk of t, is some random function. It's some random variable. But I'm going to construct t in such a way that I can promise you that the risk falls to the left of gamma most of the time. Okay, so the risk of t is a random variable. It's trained on data. But I can promise you that the random variable r of t will lie to the left of gamma most of the time. In particular, the chance that it's larger than gamma is less than delta. Okay, and you told me gamma and delta in advance, and then I run the procedure. And for whatever gamma and delta you told me, I can run the procedure to guarantee this. Okay, so we're going to train the procedure. We're going to calibrate the procedure in such a way that I can promise you that the risk is less than delta, with high probability. Great. All right. So I'll describe to you how you do that training procedure, which is kind of the key step from today. Before I do that, I'll just demonstrate what happens when you run that procedure on this tumors data. So if the user here asks for the probability that the risk, which is the false negative rate, is greater than 0.1 is less than 10%, we see that's exactly what we get. So the false negative rate of 0.1 is this vertical line right here. Okay, and the 10%, the 10% is the probability mass to the right over here. It's about 10%. It's a theorem that it's less than 10%. I can show you later. So just to repeat here, what I'm showing you on the left-hand side is a bunch of repeated experiments. So it's a bunch of parallel universes where I got a different calibration set. And the probability that I exceeded a false negative rate of 10% is kind of less than this number, 10%, as asked for by the user. Okay. All right, so I'll describe to you the calibration procedure, but before that, I'll pause for questions here.
Hi, Stephen. There's no question so far, so please move ahead.
Okay, let's keep moving. All right, so so what I'll do now is I'll talk to you about, you started with this predictive model f hat. I'm going to take that and show you how to kind of generate set value predictions from it. I'm calling that t, and that's going to be the calibration procedure. Okay, so a few more ingredients to the setting here. I'm going to consider losses or error rates that are monotonic. So monotonic is going to mean the following. If I have two prediction sets, s and s prime, where s prime is larger than s, the loss goes down for the larger set. Okay, so if I predict a larger set, s prime, the loss goes down. This was true in the tumors example. If I hand you a larger set of pixels, I am more likely to cover the tumor. And it was also true in the classification setting, the X-ray setting, where if I give you more labels, I'm more likely to cover the ground truth label. Okay, secondly, what I'm going to do is I'm going to take f hat, your deep learning model, say, and I'm going to extract a one-dimensional family of kind of set valued predictors. So there's going to be one parameter, lambda, and for larger values of lambda, I'm just going to ask you to hand me larger sets. So, you can do this however you want. I'll show you some ways to do this. I'm going to construct some one-dimensional family again from f hat. This can be done however you want, but there are kind of natural ways of doing it. And I just want the families to satisfy the following. When I kind of turn the parameter up, the sets get bigger. Okay, so I have this one-dimensional knob from small sets to big sets, and I'm going to choose where I want to be on that one-dimensional knob. In the tumors example, I'll show you what this family looks like. So for each row here corresponds to a different value of lambda, or the top row is the images themselves. So if I threshold the output of my deep learning model at level 99%, which is kind of a high level, you see that the sets are small. So I correctly get the white part of the tumor in the middle, but the red surrounding the tumor here, the red halo around it, is missed pixels. So it's true tumor that I missed. And then the black is kind of other pixels that I did not return. So in the top line here, you see the sets are very small. Okay. In the middle line here, they're a little bit bigger. You see that I'm kind of correctly getting most of the tumor, which is in white. And I have a little bit of spurious positive here in blue. Okay. And then if I change the level of lambda to make even bigger sets, I get the output on the bottom, where I'm returning almost the entire image. I'm returning these entire blue regions plus the white regions, which is too big. So here I have small sets, here I have medium sets, and here I have large sets based on where I threshold. All right, and the last ingredient here is going to be a pointwise upper confidence bound, or a confidence interval for the risk. So I can get a confidence interval for the risk based on these holdout points from, say, a concentration inequality. But this is where I use the calibration data for each value of lambda. Okay, so for each value of this one-dimensional parameter, I have the upper end of a confidence interval, which I'm going to call r hat plus. So r hat plus is guaranteed to fall above the true risk, which I don't know, with probability 1 minus delta. Again, it's a confidence interval for this risk. It's going to come from something like a concentration inequality. All right. Okay, so I finally get to show you the procedure here. Let's look at the plot first, and then I'll parse kind of the theorem below. So the way the procedure works here, I'm plotting on the y-axis, I'm plotting the risk. So, and on the x-axis here, I'm plotting lambda. So remember, lambda is the parameter that controls the size of the sets from small sets to large sets. In black, I'm plotting the true risk function. So I as the analyst do not get to see the black curve when I have a data set. Only nature knows the black curve, but I'm plotting it here so you can see it. What the analyst does get to see is this gold curve here, which I'm calling r hat plus. So r hat plus is constructed from the data, and the kind of guarantee about r hat plus is that it lies above the black curve, or at least each point lies above the black curve, with probability 1 minus delta. I'll show you how to construct r hat, but r hat is the thing that the analyst gets to see. So once you have r hat, you do the following. You walk from big sets to small sets along this gold curve, and you stop when you hit gamma. So gamma is this risk level that you wanted to achieve. So you just take the smallest sets possible where you see that your upper bound is below gamma. So you walk until you hit gamma, and then you stop, and that's lambda hat. Lambda hat is the sort of value of this parameter that you're going to select. All right, so this walking from right to left is described symbolically in this equation right here. If you do that, the guarantee that I'll give you at the end of this procedure is the following: with probability at least 1 minus delta, your risk is less than gamma. Okay, so you're going to take this lambda hat that you got from the calibration procedure, you're going to deploy it on future data, and the promise is that in most worlds that risk is less than gamma. Unless you got really unlucky, that risk is less than gamma. Okay. All right, so the proof here has kind of two main ingredients. The first one is this monotonicity. So the way that the problem is set up, I know that the risk is kind of decreasing in lambda here. I don't know what it is, but I know it's decreasing. Because it's monotone, I only need point-wise concentration results. So I only needed an r hat plus that lies above the black curve at each point. It doesn't need to kind of simultaneously lie above the black curve. That's good because the simultaneous envelopes are harder to build than the point-wise envelopes. Okay, so yeah, I'll sketch the proof here. I have a little bit of time. So the way the proof works, it's not too hard. You look at this point, this critical point where the black curve intersects gamma for the first time, and I'm going to call this lambda star. Lambda star, again, is not known to the analyst, but it is known, when we're doing the proofs. So you look at lambda star and you say, what happened at lambda star? So because this curve is monotone, and based on the definition here of lambda hat, the only way I can violate risk control is if lambda hat happened to fall to the left of this critical value lambda star. Okay, so I only violate risk control if this guy happens to be over here somewhere. But that can only happen if my confidence interval or my upper confidence bound at lambda star was violated, right? So right now my upper confidence bound is here, so I'm in great shape. I know that lambda hat is to the right, which means it's valid. The only way lambda hat can be invalid, can fall over here, is if this upper confidence bound at this critical value lambda star happened to fall below gamma. Okay, and that can only happen with probability 1 minus delta because this is a point-wise valid confidence interval, so I can only violate the risk with probability delta. I can only miscover this point with probability delta. Okay, so in conclusion, the probability that lambda hat falls over here on the left is at most delta. All right. Okay, so I will kind of show you this procedure on our tumors data with kind of, very concretely, how do I run this on the tumors data? Okay, so first what I do is I take 1,000 extra holdout points. So this is my calibration data, the points I've been telling you about. And I just look at the risk on those 1,000 holdout points. So remember, the risk in this case is the false negative rate. For every value of lambda, so kind of for each size of set, I just look, what is the false negative rate on my 1,000 holdout points? I'm plotting that in blue on this curve here. This curve, again, is on the x-axis is lambda from small sets to big sets, and on the y-axis is risk, which is the false negative rate. Recall, I'm asking for a false negative rate of 10%, which is this horizontal line. Okay, so in blue, I just empirically look at the false negative rate on my holdout points. And I plot that, for example, here. Now, in order to make a valid upper bound for this blue curve, I'm going to use some sort of concentration inequality. So you can imagine using Hufting's inequality here, which just requires that I add log 1 on delta over 2n, square root of that, to my empirical risk. So an upper bound, so the false negative rate is between 0 and 1, so I can get an upper bound with Hufting's inequality. The upper bound is the following. I look at the empirical risk, so just, the false negative rate on those 1,000 points, and then I add this constant due to Hufting's inequality, and then it's a theorem from Hufting that this is an upper bound. Okay. All right, so I plot that. That's the gold curve here. I plot that in my computer as the analyst. And I just walk along until I hit 10%. I walk along until I hit gamma 10%, and then I stop, and that's the level that I'm going to select. So in this case, it's kind of this middle level of set size, the one that has the good performance we've seen previously. Okay. All right, so I'll pause here for any questions before I move on to the next topic.
Hi, Stephen. There's no question, so please go ahead.
Thanks, Luba. All right. So, okay. So in the previous slide, I showed you this kind of calibration procedure. I just look at the empirical risk on the holdout set, and then I make a confidence interval with a concentration inequality. I told you about Hufting's inequality on the last slide, kind of for simplicity, but it turns out there are better concentration inequalities to use, or you can get tighter concentration inequalities with something other than Hufting's inequality. So in practice, we recommend using those. I don't think I'll have time to tell you about the details, but I'll kind of sketch why you might use something better than Hufting in this case. So if I have a bounded random variable between 0 and 1, let's look at this top left panel. Oh, I should say this material is from this really great paper by Wildby Smith and Ramdas from last year. It's not a new result. We're using a concentration inequality. Okay, the reason you might want to use something other than Hufting's inequality is that Hufting is kind of assuming the worst case variance between of the random variable. So if I have a random variable such as this beta 1030 that is kind of more tightly concentrated than the worst case would be binomial on the edges, Bernoulli on the edges. The empirical mean will concentrate a lot faster than Hufting suggests, because Hufting doesn't know about the variance and it doesn't update if the variance is small. So if you instead kind of empirically figure out what the variance of this is, and then adjust your confidence intervals, you make them narrower when you know the variance is smaller, you can do a lot better. That's sketched in this center and right panel. So in blue is empirical Bernstein, and then in green is this, what I'm calling the WSR method, this method proposed in this paper, which has really great performance in our simulations. So it has much narrower confidence sets than, say, empirical Bernstein or Hufting's inequality. All right, so you can use better concentration inequalities, but conceptually they fit into the procedure at exactly the same place Hufting did. It's just you can do something a bit more powerful. All right. If your loss is unbounded, you can't use concentration results typically, but you can appeal to sort of asymptotic results. I'll refer you to the paper for those details. Okay, so lastly, I'll go through a kind of a set of examples here of different cases where these prediction sets can give you some sort of interesting uncertainty quantification. I told you about the tumors example in some detail, so I won't revisit this one now. But I'll talk about a related problem, which is multi-label classification. Okay, so in multi-label classification, if you look at this top left image, I'm given this image of the scene. And in this case, there are kind of two correct labels, not just one. There are two labels associated with this scene, and the two labels are car and parking meter, okay? Similarly for the other images. So what that means is the correct label here is a subset of the label space. In this case, the label space, there are 80 possible labels, and then the kind of correct output is perhaps multiple labels, a subset of 1 to 80. I'm again going to use a sort of deep learning model f hat. And then what f hat is going to do is for each of those 80 classes, it has this guess between 0 and 1, this model probability that guesses how likely or not each class is to be a kind of true class of that image. So in this setting, you're always returning sets. I'm now going to kind of calibrate those sets, and I'm again going to kind of control the false negative rate. So I'm going to return sets in a way where the false negative rate is controlled on the future test points. So the loss here is the same as it was for the tumors. If I looked at this top left image, for example, the loss is the false negative rate. If I looked at this top left image, my model outputs person, car, skateboard, and bicycle. Bicycle is a spurious positive. Person, car, and skateboard are correct. Bench is a missed positive, so or like a false negative. So bench is a correct label that was not returned. So in this case, my loss would be 25%. There were 4 correct labels and I got 3 of them right, so my loss is 25%. Okay, now I'm going to kind of build a family of set predictors in exactly the same way. I'm going to take my deep learning model and I'm going to threshold the output at some level lambda. There's a minus here because of the directions of the problem, but it's not important. It's thresholding the probability at some level, say 20%, 50%, 80%. Okay. And then what I'm going to do is I'm going to figure out what does that thresholding need to be in order to control the false negative rate on future data. In this particular case, I can again kind of compare to a conformal prediction baseline. The conformal baseline is going to say I want to get all of the correct labels 90% of the time. So that's the conformal baseline. On the bottom, I'm plotting the results. So let's look at the left panel first. The left panel, I'm plotting a histogram of the risk across kind of different trials. So each element here is a different split of the data where I have some calibration data that I then evaluate on the remaining data. These 3 procedures here are different variants of the risk controlling prediction sets. that use different concentration results. So yellow here is using the Hufting bound. Green is using the improvement to the Hufting bound that I alluded to briefly. And then blue is using the central limit theorem, so it's not a finite sample result. You see that green is a bit better than yellow, and blue is even a bit better still, but it's not finite sample, no finite sample guarantees. But in any case, they're all controlling the risk relatively tightly around this desired threshold of 10%. Okay. So this is exactly what we asked for. We want it to be to the left of 10% false negative rate, and that's what we see. The conformal prediction baseline is being much more conservative. This is similar to what I showed you before. The conformal prediction, the error rate that it's trying to control is it's trying to get all of the correct labels right. And in this case, it's trying to get all of the correct labels right with probability 90%. All of the correct labels of a single image with probability 90%. And what that translates to is much more much lower risk, which means more conservative performance. On the right side, I'm plotting the size of the images that you output, or the size of the sets that you output. So easier, some images have a very small number of sets, some have big ones, as we see here and here. All of the risk controlling prediction set variants, so all three versions are about the same. You see that the conformal prediction sets here are bigger. Again, it's because they're targeting a stronger or a kind of like stricter error control notion. So conformal prediction in red is returning larger sets and being more conservative. Okay, lastly, I'll show you an example from hierarchical classification. So the setting here, it's a classification problem where each output has only one label. In this case, there's 1,000 labels. The distinction here is that there's a structure on the labels, and that structure is that the labels are leaf nodes on a tree. So this is, it's called the word net hierarchy. It's just a tree on the labels of the ImageNet label set. And the reason this is interesting is because now prediction sets have a new interpretation. Prediction sets can be interpreted as instead interior nodes of this tree. Okay. So if I look at this top right image here, the correct answer is consommé. The model outputs hot pot as its point prediction. That was incorrect. But the kind of adaptive model, the one that kind of chooses a layer of resolution based on the data, instead outputs dish, this center image, which is correct. It's correct, it's just at a coarser layer of resolution. Okay. So you see that in the tree here. The model guesses hot pot, which is wrong. The true answer is consommé. But if you calibrate it, you can just tell, the model can just return, say, dish. You can say, I don't know what type of dish it is, but it's a dish. I'm confident it's a dish. Okay. So we're going to use a loss function that kind of, you return a prediction set. It has some sort of error rate. The error rate in this case is going to kind of depend on the geometry of the tree. So the farther away you are on the tree, the worse an error is. If you contain the correct label, then there's zero error. And I'm going to construct the nested sets in a special way. I'm going to construct them such that they're always subtrees. Okay. So because they're subtrees, because the kind of set of labels I return is always a subtree, I can summarize that information by returning just the interior node, right? As I did over here. I could return you the set that says pizza, meatloaf, burrito, pot pie, hot pot, consommé, or I could equivalently just say that's a dish. Okay, so that's because we're going to only return subtrees, we can kind of summarize that information by returning an interior node of the tree. Okay, so we ran this calibration procedure. I'm showing you the risk here on the left, which is again the kind of distance away I am in tree space. I'm targeting a level of 0.05 in this case, and that's what you see. So the three colors are again three versions of the risk control and prediction sets, and you consistently fall to the left of the target level 0.5. On the right here, I'm plotting the height, which is kind of the layer of resolution of my final prediction, and you can see it varies kind of from 0, which would be point predictions, to very uncertain predictions that are 8 layers up in the tree. All right, so with that, I'll kind of conclude here. So just to recap, today we talked about sort of inference for prediction tasks via prediction sets. So we had set value predictions with certain error rates associated with them. We had these kind of finite sample risk controls for any predicted model and any unknown distribution. And we talked about sort of different error rates you could control, such as the false negative rate for high dimensional outputs. Okay. from a math perspective, what's going on here, the reason you can do it is because there's a certain monotonicity structure in the problem, which is that like bigger sets means lower loss. And then together with these point-wise concentration results, you can get finite sample guarantees. Okay, so other settings, like other things you could sort of do with this, there's a variety of kind of different prediction problems where you might want some sort of error control that we haven't worked out all the details from, and you could sort of use this technology in various places. In conformal prediction, there's kind of a whole line of work on the right way to use what's called the non-conformity score, which in this case, the analog would be the family of nested sets, that one-dimensional family of predicted sets that you're going to use. And there's kind of important design, or I'll maybe say engineering considerations into how you construct that, right? There might be other risk functions you'd be interested in here besides the one I've used in this talk. And then I would say kind of large theoretical consideration here are what are sort of lower bounds on the risk. Okay, so sometimes in say conformal prediction, you have an upper bound on the coverage of your prediction sets. You might be able to get analogous results here, which would be interesting. All right, so with that, I'll wrap up and hand it over to Professor Vovk.
Thank you so much, Stephen, for the fascinating talk. We have a question from Armin Schwartzman. Let me let you unmute yourself, Armin.
Great.
Thank you. Well, I thought it was easier just to speak than to write everything into the chat.
Sure.
Great talk, Steve. Very good work. This is definitely an important problem. Just have a basic confusion. I think it's very naive, but basic. So if I take the risk, let's say the false negative rate in this case, and I can estimate it by a holdout set, by a cross-validation, bootstrapping, any of these methods. So if it's either cross-validation or bootstrapping, I'll get a distribution of possible values of this false negative rate, and I could take a quantile of that distribution. So that's a very naive approach, but why wouldn't that work? And how is that different from what you're doing?
Yeah, thanks for the question. So what Bootstrap is measuring here, in contrast to what I presented, but also in contrast to say all of conformal prediction, Bootstrap is measuring the sampling variability of some output, which is including kind of the sampling variability in the model fitting and then your evaluation. Okay, so Bootstrap is asking, like, when I shuffle the data and say like refit the model, what changes? Here I'm asking a slightly different question, which is just for one fixed model, what can I tell you about the predictions of that kind of fixed model? So I mean, you could use Bootstrap to get sort of maybe some notion of how much things are varying in the problem. But again, Bootstrap is telling you how much does my model prediction vary, which is not the same question as, you know, how good is my model prediction? Yeah.
Would cross-validation suffer from the same problem?
Oh yeah, so if you're using cross-validation to estimate prediction error, I would say the distinction here, so cross-validation can estimate global prediction error, right? It tells you that on average, I got 80% of the images wrong. What we're doing here is like, we're doing something a little sharper, which is for each individual input, I'm giving you some kind of adaptive notion of uncertainty. So I'm telling you some inputs are high uncertainty, some inputs are low uncertainty, rather than just returning a global estimate of prediction error. Yeah, thanks.
Okay, great. Thank you, Stephen. And now, Vladimir, are you there?
Yes, yes.
Great. So now we're over to Vladimir Vovk for the discussion. Please take it away, Vladimir.
Okay, thank you, Will. Okay, so I enjoyed this talk very much. I hope you can see my screen, maybe not. Let me share it. Okay,
yes,
can you see? Oh, you can see it now. Good. Okay, so let me start from listing what I liked most about this paper. So I think it has several great contributions. So one striking thing is that you don't need uniform convergence as irrelevant. So in mainstream machine learning, in the Vapnik-Chervonenkis approach, it's important, But here, under the restriction of monotonicity, it isn't. And of course, it makes sense, since we are talking essentially about the borderlines, the borderline lambda, borderline value of this parameter, where the risk is gamma. We have a careful exploration of concentration bounds. It's surprising how bad holding is. Interestingly, if your loss is just 0, 1 loss, taking two values, you don't need any concentration bounds. You can just invert the binomial distribution function, and then it works, and it's ideal. But of course, when your loss function is more complex, it becomes more complicated, and it's interesting. Newer methods work so much better. In the paper, but not in the talk, the authors explain how you can achieve efficiency if you can estimate the conditional probability of the label given the features. So it's interesting that even if your estimate is very bad, you still have validity. You always have validity. But you will have efficiency if your estimate is good. So it's very similar to what people do in conformal prediction. Sometimes it's called frequentizing. So the model doesn't have to be Bayesian. It can be just some narrow parametric model for estimating the conditional probability. But even if it's very, very narrow, still the final procedure is valid under the IID assumption, under some non-parametric assumption. And of course, there were four exciting applications. But I have a few questions for Stephen or the authors in general. So one is about slides, I think it was slides 8 and 21, why conformal fails. Because it's trying to fully cover 90% of examples. So I learned about the precise procedure earlier today, so maybe my objection is naive. But to me, it looks that conformal prediction should be qualified here. I think it was the author's choice to make the method brittle, as Stephen said. So here I say fragile somewhere. The conformity score used in this setting as S of xy. So here x is the features of our observation, and y are the true pixels where the tumor is. So to define this conformity score, we just take the minimum of the probabilities or likelihoods output by our model, our deep neural net, over the true pixels, the true tumor pixels. So we have minimum, and I think minimum, it looks fragile to me. So even 1 pixel can change a lot. If you misrecord 1 pixel, it can change this conformity score a lot. So I thought a safer thing to do, maybe just to take some 10% quantile, maybe not the exact minimum, something slightly more robust. And you could call it, you could say it's a gamma quantile. So it would add another parameter here. So you would have delta and gamma in this procedure. So maybe the pictures in a way can become more similar to those on slide 9, on the next slide, where Stephen illustrated his or their methods. So here there are complications. I don't have time to talk about complications in this procedure, but if you could tell me what happens if you redefine the conformity score, it would be interesting. So next, so there was a slide about hierarchical prediction. I think it's one of the most exciting applications. I liked it a lot, but what I found awkward about it is that it involves the most likely class. It's possible that even maybe you have lots of classes, and maybe even the most likely class is still unlikely, and maybe the true class it gets split into lots of some very subtle subclasses. All of them have very small probability. And I think considering this most likely class, it's almost forced on us by having this nested family of prediction sets. And it would be interesting for me to know the author's feeling about it. Do they think it's a real difficulty? And if so, are there any ways to overcome it, any ways around it? Next, can you make the author's procedure in a sense more conditional? So people have been talking about conditionality in several papers, several recent papers about conformal prediction, and I think it's a very interesting topic. So if in Vinit Subramanian's book, for which I wrote a chapter 2, I tried to give some a scheme of notions of conditionality. So I came up with this very, very crude conditionality cube. What can you condition on? You can condition on X, on the features. You can condition on Y. So these are pure notions of conditionality. You can condition on X. You can condition on the label Y, and you can condition on the training set. In conformal prediction, people often don't condition on the training set at all. But this paper does. It conditions on the training set. But this paper doesn't condition on X and Y. And it would be interesting for me to know if there is any scope in developing these procedures in direction of conditionality. So you can't condition on everything. You can't condition on the training set, on X and on Y. Because no randomness is left, you just can't do anything. In conformal, just in basic conformal prediction, it's unconditional. So it's you unconditional. You don't condition on anything. So it's this vertex of the cube. So I think what is okay. So first, X conditional validity is more popular, I think, where you condition on the features. So that, like in medicine, I know that your prediction is valid, or your bound on the error rate is it's working for me. It's not just true on average, but it works for myself. I know that it's done for myself. It's fitted to me, but I'm not sure if the condition of validity, if the error bound, if it's applicable to me or not. So there are some serious difficulties here. Why is Y conditionality is important? Where Y is label. So surprisingly, it's also important, and you can to understand why it's important. You can imagine that you have a different the same number of different patients. So some patients have normal lungs, one third have COVID-19, and one third have a pneumonia. And suppose at some confidence level, like 1 minus delta is 90%, the risk of your predictor is 0 in the normal and pneumonia cases, but it is 3 in the COVID-19 cases. And of course, if you say that the overall risk is 1, people are not going to be happy. Probably nobody is going to be happy. So my question is, can you make these confidence sets Y conditional, so that each class has a similar risk? Also, that in general you can control risk for different classes independently. This is what happens in conformal prediction. So when you do it Y conditional, and also when it's Y conditional, it partially solves a problem that is mentioned in the paper, which is one of the reasons why loss functions are considered. So suppose different mistakes have different cost. For example, missing COVID-19, suppose it's something very, very costly. Then you can set a different threshold for your p-values. You can, if you set a demanding threshold, then it can be different costs can be also reflected in your predictions. And the last thing, so I like this paper a lot. So it's a short note by Tom Fawcett and Peter Fletch. So it explains that there are two kinds of data sets. X implies Y, or X causes Y, and Y causes X. So Y causes X, it's a very important kind of data sets, I think, especially in medicine. For example, in medicine, Y is something like COVID-19. And of course, it's clear that the kind of disease, it causes what we see on an X-rays. Not vice versa. So the causal direction is this. It goes from Y to X. And probably if for such data sets, Y conditional validity is more important than other kinds of conditional validity. Okay, so it only scratches the surface of this beautiful paper, but it's all from me now.
Thank you so much, Vladimir. Stephen, do you want to respond? Sorry, I didn't mean to interrupt you.
Yep, no problem. Yeah, thank you very much. That was a really fascinating discussion. I think, I think it was very insightful and got pretty much everything, a lot of things that need to be done there. So I guess I'll sort of hit on the first few points, and then, with my limited time. Yeah, so the first question was, so for example, in the tumors data, can I do better with conformal? Like, is there an instantiation of conformal that would work better in this kind of high dimensional setting? And the answer is absolutely yes. So the shortcoming of like the instantiation of conformal in this case is the error rate, like I said, which was we want to fully cover 90% of examples. We could instead ask for what Professor Vovk suggested, which is maybe I want to 90% cover 90% of examples. So if I only wanted to do the following 90% of the images, I got at least 90% of the examples, I could still use conformal prediction, and it would be much better than this, and it would be reasonable. So I would say that the kind of summary there is basically whenever you have a loss function that you can reduce to a binary number, so it's either a 0 or a 1. In this case, like I got 90% of the image correct, or I did not. Whenever you have a loss function that's 0, 1, you don't need the calibration that I told you about today. You could use kind of the existing calibration scheme from conformal prediction. What I've showed you today is the same as training conditional conformal prediction when you have a 0, 1 loss. So there are ways to try to tackle this problem with a kind of loss, with a binary loss that would be a little bit better. But I would say in general, I think for this particular problem, I think the false negative rate is maybe a more desirable error control. But absolutely, you can use conformal prediction in many problems as long as you reduce it to a 0, 1 loss. And there are better ways or worse ways potentially to reduce the problem to a 0, 1 loss, to a binary loss. There was a question about hierarchical data. How fundamental is it that in the instantiation we use in the hierarchical classification, which I didn't have time to tell you today, we start at the most likely class and then grow a subtree around it. There was a question about how fundamental that is, and I don't know the answer. I mean, this is sort of related to the fact that I'm using a one-dimensional parameterization of nested sets so that I can do that calibration correctly. There might be better ways to do that, or you might want to use something richer than a one-dimensional family. I don't know the answer to that quite yet. Yeah, and then there was this sequence of questions about conditionality, which I think is enormously important in conformal prediction, and then also in this work. So there was this question about training conditional, which we are kind of already doing in this work, and then about conditioning on X or conditioning on Y. I think that conditioning on Y would be possible with this framework and would be useful. And the same with conditioning on X. I would like to say here, there's, I think this is related to this note, which I haven't read yet, about X causes Y or Y causes X. In these very high signal problems, such as in image classification, where kind of for any X, there's really only one Y, there's only one correct Y. Or put another way, the distribution of Y given X is really a point mass for the true distribution, not for my estimate. I'm not sure how to think about conditioning on X as kind of like conditional on X validity, because I think the only way to have conditional on X validity is to have a model that, you know, perfectly gets the right answer, essentially, for every single X. So I think thinking carefully about what conditional on X validity means with problems where kind of you have essentially infinite signal, or the distribution of Y given X is essentially deterministic, I think is kind of an interesting open direction right now. But yeah, I won't have time to give any more thoughts there, but thanks very much for the great comments.
All right, thank you so much, Stephen. And I'm going to stop the recording now.